Okay, so I get sent this question. It's a great question to talk about, okay? I know a lot of people usually do have some issues with this. So there's essentially three ways of representing. This is post-lecture, chapter 5, question number 3, by the way. Okay. There's essentially three different ways that you need to familiarize yourself with of representing three-dimensional structures in a two-dimensional media, right? Which is print. There is, of course, the perspective drawing. And so these will be perspective formulas right here, right? And you have your wedge coming out towards you, you have your dash going away from you, and you have the line in the plane with the paper, right? They're actually, in many ways, the least accurate of the three-dimensional and two-dimensional, right? Three-dimensional drawings, let's call them. Okay. The Fisher projection is a great way of representing enantiomers, right? So when you're talking about chiral centers, Fisher projections are wonderful. And this is a Fisher projection. And remember, the vertical is going away from you, right? So things on the vertical, like this and this would be in the plane of the paper, this would be going away from you, and this one would be going away from you, right? And then the ones going horizontal are coming out towards you, okay? And so this and this are coming out towards you. And whenever you're doing this, you're always going to be talking about a chiral center, right? So you always just look at that chiral carbon, and that's the perspective. You look at the next chiral carbon, and you don't go down, 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 away, 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 right? You're only looking at one chiral center at a time, okay? So you look at this chiral center, and these come out towards you, right? And then these go away from you. Can you see that okay? Okay. And it doesn't really tell you anything about the geometry around non-chiral centers, right? Like so. These are non-chiral carbons, right? And they don't tell you anything. Because it just doesn't care, right? There's no chirality there. Not worth discussing. Okay, Newman projections can tell you a little bit of information about chiral centers, a little, but they're really useful for conformations, okay? And so you're going to be looking down in a Newman projection, a bond, and you always look down a bond, right? So for example, typically in a Fisher projection, your numbers of carbons is going to be numbered going downwards. So this would be 1, 2, 3, 4, 5. Okay? Is that making sense? And so let's say we look down the 2 to 3 bond. The thing in the front right here would be the second carbon. This one right here, right? The thing behind it, the circle represents the thing behind it, right? Is this carbon right here. Can everybody see that okay? Okay, fantastic. Okay, this shows you the two different conformers of this, right? So this would be the eclipsed conformer. It's eclipsed because these bonds are eclipsing each other, aren't they? Okay. How I order these groups around here is I need to act like I'm looking down this bond, right? So remember, these are up, up, and up, right? Okay. So if I looked down this bond, so sort of orient yourself, think about orienting yourself so you're looking down that bond. My left-handed side would be my OH typically, right? Okay, and that would be on top. My right-handed side would be on top, this H, right? Okay. Another way of representing that would be flipping it upside down like so. They made this a little more difficult by drawing these groups downwards. But essentially, what you see here is you have a triangle. See that? These two are up. This one's down, isn't it? So you need to represent this as a triangle. So this will be two legs of the triangle going in one direction. Can you see the triangle there? Okay. And then the third leg of the triangle going the opposite direction as the other two would be this CH3, right? Okay. Does that make sense? Remember, these are up, that's down, isn't it? So it makes a triangle. Okay? With the base of the triangle being coming towards you. The point of the triangle going away from you, right? Okay. These also make a triangle, don't they? Again, this is coming towards you as the base. Going away from you is this CH2, CH3, right? And so again, you have your base of your triangle, like so. You have the tip of your triangle, like so. Okay. These triangles are going to be essentially base to base, aren't they? So think of a piece of paper. You have two triangles that make the piece of paper, right? If you fold it, what happens? Well, your tips line up perfectly, don't they? And then your bases, well, they line up, those corners, don't they? Whatever was next to each other is still next to each other, isn't it? That's all you're doing. You're essentially folding your square, aren't you? Is that making sense? Are you starting to see that and connect that to physical objects? You can sort of use your hands if you want. You have your points of your fingers, right? Those would be your base of your triangle. And then you have the palm portion of your hand. You can fold those together. You notice the bases still stay lined up. See that? Okay. And that's what we're doing here, okay? So that's the eclipsed conformer. Everything stays nicely lined up, okay? The staggered conformer, you're just going to rotate a 60-degree rotation, right? So literally, you just rotate one of the triangles, okay? In this case, we rotated the back triangle. See that? We rotated it one step right. So this goes over here, right? So the C2H2, CH3 is over there. And then you just write in your triangle again. See that? So on the left of that CH2 is the hydrogen, right? So it goes up here. Or again, you just rotate all these clockwise. One tick. Does that make sense? Did anybody get confused? Please let me know if you did. Okay. Okay. I'm going to assume everybody's okay. Okay. And again, you can help yourself with your hands if you want. So they're the triangle, right? You have your tips of your triangles or your tips of your fingers. You overlap them. You have your thumb on one, thumb on the other. Is representing the two sides, right? So eclipse would be them directly overlapping, where the fingers overlap the fingers. And then you put them so they're sort of perpendicular, not quite, 60-degree rotation. And then you would see what a staggered formation looks like. Okay? Okay. Feel free. All right. So that's essentially what you do for all these, okay? So in this, you have your Newman projection you're starting with in this case, right? Okay. So right here, you have a triangle, and this is that front one, right? Okay. And what you can do is you can just directly draw that in with the triangle just as we talked about, okay? That first one does really, really easy, okay? Okay. So you just draw that in. Bam, bam, bam. It doesn't matter if you get that one the wrong orientation. There is no wrong orientation, okay? Remember that if I reflected everything in this Fisher projection, I would actually still maintain everything, okay? If I rotated the whole thing. Remember that? So if I rotate the whole thing, it's still okay. Okay. Okay, so I did that one first because it's easiest, right? And then the next one I'm going to do, well, all right, so we have our CH2OH on the bottom, And that's still going to have to line up to the bottom, right? That's no problem. Okay. But how do I assign where these are? Notice that because we're staggered, we've rotated that bottom all the way around, haven't we? See that? Can you envision it in your head? So if this was eclipsed, it would be like that, right? Okay, we've rotated 180 degrees. There's two ways to do this. You can either rotate it back up into the eclipse where these are overlapping, and that way it's my bent square, right? My folded square. And then it's really easy to assign these groups. Or you can understand, because we've rotated them 180 degrees, they flip-flop sides, haven't they? Okay? Which means we have to flip the sides. So the OH group is on the left up here. It needs to be on the right. The H group here, it's on the right. Well, it needs to be on the left, doesn't it? Because 180 degrees means I flip-flop the sides, haven't I? Okay. Okay. Alternatively, you can just like rewrite this. Okay? So you just rotate this up. That would put the hydrogen overlapping this hydrogen, right? And that would put the OH here overlapping this OH. That's personally how I find it easier. But if you're a little easier memorizing, 180 degree rotation, well, that means you flip-flopped, right? You flip sides. Okay. Did anybody get lost, or everybody okay? Okay. Yeah, please do let me know if you got lost anywhere, even if you're on video and you just need to email me a question. Feel free. Okay. This one right here that we're on, part B? Okay. Okay, so now we have a Fisher projection, and we're giving it right here. We're going to make a Newman projection of this. We're going to view it down the C2, C3. By the way, the C2, C3 is the rules of Fisher projection actually mostly mirror the rules for apparent and numbering carbons. Remember, the most oxidized one is typically the one with the highest priority, right? And then the functional group, you want the lowest number on the functional group. And that sort of mirrors Fisher projections, okay? Most of the time, their numbering will be okay. Assuming everything was done right. So your C2 and C3 are what? This would be C what? 1. That would be C. 2, and that would be C3. So your Newman projection is going to be looking down your bond of C2 will be in front, C3 will be behind it, right? Okay. And so I need my Newman projection. Oh, it did it to me again, didn't it? What is what? I think this faded out ones are in the back, right? Yeah. I hate how I get that. It doesn't look like what you guys get. It's just weird. It's really hard to figure out, man. Anyways, these faded ones, these are in the back, right? And these ones will be in front. Okay. And that is correct. So our C2 right here is going to be in the front, right? And again, we should put a triangle. If we want to make our lives easy, we will put it so it is a upwards facing triangle. Okay? And so on the top, we'll have CH3. On the bottom right will be, well, bottom right is BR, isn't it? And remember, these are already triangles, aren't they? Okay? Because this is away, this is towards us. It's already a triangle. And that right there is bottom left, isn't it? Then we have the bottom left. So we have our first triangle, don't we? Okay. So yes, the eclipsed are the easiest ones to deal with, right? Because then we can just mirror the triangles. No problem. But we know a rule to help us out when we're not eclipsed, right? When we're in the stagger formation. Specifically, we can make this pretty easy on ourselves by doing 180 degrees staggered formation, right? When we're doing 180 degrees, well, this one will be on the opposite side, won't it? So we'll have the CH2, CH3 going to the bottom, right? Okay. These, though, because we've rotated 180 degrees, they always have to be flipped, don't they? Yeah. And so we look at the NH2 and H, and they have to be flipped, don't they? Yeah. So our H is going to be on the left. Our NH2 will be on the right. Yep, we flipped them. And one of the things you can use to help yourselves keep in track of this and in mind, exam? Yeah. Hopefully you did good. All right. Is that in these, they're on opposites. This would be like up and down, right? Literally, it's up, down, isn't it? In these, they're on the same side. They're both up, aren't they? Okay? So we're literally flipping in 180 degrees. Up is going to down, right? Meaning when we flip things 180 degrees, left is on right, right is on left. This is going from Fisher projection to a Newman projection. And I'll go ahead and re-sum up what we just talked about. So whenever you're looking at these, the easy way to deal with these is to think of them as a square, like a square piece of paper, okay? And so when you have a Fisher projection, when you're going from a Fisher to a Newman, you're folding the square. So point is on point, okay? And that would give you an eclipsed conformation because this would overlap that, wouldn't it? Okay. And so eclipsed conformations are super easy to figure out because everything just lines up. This lines up to that, this lines up to that. Everything's lined up, right? Keep in mind that these are triangles. So this is up and up. That'll be the base of a triangle, right? This is going away from you. That would be the tip of the triangle going away, right? And so it's literally a triangle pointing away from you. Same thing down here. This is literally a triangle pointing away from you. Okay? When you look at Newman projections, they're triangles. They're a triangle and another triangle. See that? And so if this was eclipsed, you could literally just write this in as a triangle, like so. I'll show you right up here again, right here. So this would be the example one, this would be it. That would be eclipsed, right? So you literally just write in the triangle, see that? It's the exact same thing. Same directions, everything. Yeah. And then you have your folded over triangle, right? At the bottom. And again, you just write in that triangle, same directions, same everything. So this overlaps the CH3. The ones that are on the same side overlap each other. Okay. But when you're staggered, you have to rotate everything, don't you? Okay. Specifically, if you're staggered so it's up and down, so CH3 is up, and then the CH2, CH3 is down, like this case right here, well then you're not overlapping anymore, are you? You've rotated it 180 degrees. So, if we rotate something 180 degrees, what was on the left side will be on the right. What was on the right side will be on the left. So the first one, the top one, you just write in. Because it matches, right? Top, top. Right, right. Left, left. No problem. The second one, though, is going to be rotated 180, right? So it's going to be flipped. So we write CH2, CH3 on the bottom. The one that was on the right will now be on the left. The one that was on the left will now be on the right. And that's it. And again, keep in mind, this is because we're looking down the C2 to C3 bond. right? So when we look down this bond, we're looking down triangles. And they would match up like you folded a square piece of paper, right? It's literally what you're looking down. Okay. Okay? Everybody okay? Understand what we're doing there? Okay. And check out the other video where I did this one, going from Newman to Fisher, but it's not more complex. It's same thing again. Do you guys want to try one more? Okay. So this right here then will be a perspective drawing one that we're going to go into a Newman. Okay? And so again, keep in mind, we're going to be looking down a bond, right? The C2 to C3 bond, typically you'd go with your most oxidized one. That would be your 1, then the next one would be 2, the next one would be 3, and so on. Okay? Okay, so what I would always do is I'd take that one and put it on top. Carbon being on top is sort of the unofficial, well, it's actually supposed to be that way. Okay? It's sort of a, it's like lining up your sentences when you write paragraphs, right? Makes life easy. So we put that COOH on top of our Newman projection. Remember, this one will be the one in front. This one will be the one behind that. When we do a Newman projection, the things that come together into a single point are the front. The circle with the things off of it are the back. In mine, it shows it faded and it connects all the way through, which is stupid, but it is. In yours, it actually does it right. Okay? Where it only connects to the circle. It doesn't go through. Whatever. Anyways. So this is again a triangle, isn't it? Do you see the triangle? This right here is the top, right? This right here would be the left side. Sort of orient your bodies down it. So you're orienting like looking down this carbon, right? So you turn your left shoulder in towards it, you turn your right shoulder to the right side, to the front, coming out. Okay. So you're looking down that bond, right? So that means this is the top. This is on what side of the top? The left. It's your left hand, isn't it? Okay. This one will be your right hand, right? Okay, so it's COOH, top. This one going away from you, that's your left. This one going towards you, that's on your right, isn't it?
On the computer, how do you make it COOH?
You just go carbon and then attach oxygens. You don't actually have to represent the geometry. Okay. Because the geometry of that doesn't matter. Okay. Did you guys need me to finish this, or do you got it?
Okay, this how you do it? I don't know.
That's fine. Yeah, you can just put it in like you normally would. Yeah. You can also put, there's a place you can do condensed formula that has like a little condensed formula on the left, and you can actually type in condensed formulas. But honestly, if you just put in carbon with a bond to oxygen, bond to the OH, double bond oxygen, yeah, that's fine. You don't have to do this COOH one, okay? As long as you don't put any geometry in, it's fine. Okay, so this one right here, does everybody understand how you do that? Again, you're looking down this bond, right? This would go down to the bottom. This would be on your left side, top left. This would be on your top right. Okay. Everybody see that okay? And you get how you just look at them as triangles, right? Yeah, they're little triangles. Okay. Okay, you said D? All right. So sort the perspective formula and Fisher projection corresponding to the bin representing the Newman projection of the same compound. Okay. No, you.
Didn't work. I don't know. I
Okay,
don't know.
I'll have to look at your thing and we can.
I mean, maybe it's wrong, but I can't comprehend it.
No, I'll look at your thing and see what's going on. Okay. Just bring it up to me in after class. Okay, so here's we're matching them, right? That's all we're doing. Okay. So we have little bins down at the bottom. They have oh. Really? Sort the perspective formula and the Fisher projection corresponding to the bin representing the Newman projection of the same compound. So it shows you this one, right? The Fisher? Okay, that sentence doesn't say what it is. Those are not Newman, are they? There is not a single Newman projection in there. So I had to reread it for a second. Okay. Anyways, we have Fisher projections. We're trying to match them up with perspective drawings, right? Okay. And so again, we're going to look at the Fisher projections, and then we need to figure out our triangles, right? So here we have a CHO, and on the bottom left of a triangle with this on top, you would get an NH2, right? Yeah. One of the easiest things you can do is just take your hand, put your fingers pointing towards that CHO, right, which is on top. Your thumb then would be the NH2, right? And the other side, you don't really have to keep track of it because 2 things is good enough. It would be the H, right? Okay. That gives you freedom now, right? So what we're doing here now is when we look at perspective drawing, we're going to be rotating it so that our thumb is going into the paper, right? Our fingers stay pointing topwards. And then the palm portion will be coming out, right? Okay. We look at these, and what the first thing you notice is, do any of these other ones have CHO? So that one's really easy, right? I know. So if none of them have CHO on there, then...
It's top right. It's hard to work.
The Fisher?
Well, I think that's a CHO.
Yeah, the Fisher has CHO. Oh, okay. Can you guys remind me, does this have the perspectives down in these bins? Or does it have the Fisher? Because the question is not written in a sentence that actually makes sense. Okay. So if it's the perspective down there, then yes, you have 2 Fishers that both have CHO in them. Right there is the other one. What the hell? Here, let me see this. I'm gonna switch views real quick and see what the hell's going on, because there's actually something really, really weird going on. Where am I?
Yeah, you gotta be far.
Oh, okay. That's why I'm not seeing this. Okay. There we go. Okay, so the first thing we should look for is CHOs. Wow, that really did not have the right representation, did it? No, that really was messed up. Okay, so the first thing you can do is you can actually eliminate a lot of options by just looking, does it have the functional groups I want? For example, CHO and NH2, right? So I have a relatively limited set of things I need to look at then. So I go through these, I look for the NH2, well that has an NH2, and COH, right? So that's a possibility. Then I look through here and I go, nope, that's another possibility right there, isn't it? Okay, and then I continue looking through, and finally I get my last possibility, don't I? All right, so those 3 things are possibilities. Now I need to do my geometry. So again, it's always easiest to look at the first one, right? Because that's the triangle that points upwards. Okay? So CHO should be on the top. On the left side would be an NH2, right? On the right side would be an H. And that would be my top portion of the fissure. I'll look at my top portion here. Yeah, it matches up. I look at the next one, and yeah, that matches up so far, doesn't it? Finally, I'll go ahead and look at my perspective. Remember, it's like this. I take my fingers. If I rotated that, yeah, that would be pointing into the page for the NH2, right? See that? And so that's pointing into the page with the NH2, isn't it? So far, I'm good. All three of those would match, right? Okay, so the next part I have to do is I have an eclipsed form of this, don't I? Okay, so that means that this is literally like a folded paper, right? So my top is top. On my left side is my left thing, right? On my right side is my, yeah. So my top is the CH2OH, right? On the bottom left would be my OH. So on the left side of this is my OH. So let's go ahead and do the fissures first. Okay, so my left side should be OH. Remember, they'll maintain because it's eclipsed, right? Nothing gets rotated. Okay, and so, okay, looks good, right? That one's okay, so I can drag that down. I'm not going to drag it yet because I'm afraid it'll get rid of this. Then I will be out of luck. Okay, and this one right here, well, that's not my left side, is it? It's on my right side. It's the wrong way, isn't it? What would that be? Well, that would be an enantiomer. Yeah, you literally flipped one of the groups, right? Remember, you flip two groups, and an enantiomer is born. Okay. So if we got that one's good. Yes, it does. It overlaps. I'm going to wait to put that in it. Okay, this one was also good, right? Did we check it? We didn't check, did we? Yeah. Okay, so let's check this out. Remember my hand, right? So my CH2OH, that's on the top here, isn't it? So I line up my hand. So my CH2OH, that's my fingers, right? My thumb needs to then be my NH2, or my OH, right? And then my palm area is my H again, right? Okay. So let's see. We rotate this around. So the CH2OH is pointing downwards. And what would that give us for our OH?
Would be to the inside of the paper.
Yeah, that's the wrong way, isn't it?
Yeah,
Yeah, we got it wrong way. Okay? Another way of thinking about this, if you don't want to try to play with your hands and use physical objects to mirror it, is that this right here would have these things overlapped, right? So that means my NH2 and OH, they should be on the same side, shouldn't they? If they were overlapping. See that? So if I'm overlapping, you can rotate these things. So I'm overlapping, right? What would happen? God, that is terrible. All right. We may need to draw this out. Ooh. Okay. That noise is absolutely awful. Yeah. I can't even hear myself think. Okay. Did you take them in this room? This room's really bad. Oh, it's not great, but I teach down there on that side, and it's so much better than this side because the compressor's here. Oh, it's that droning. All right. So if you look at this, let's write this, okay? Let's print screen. Get this over here. That'll be easier. Okay, so we're looking at this one right here. Okay. In this, these things are represented as being overlapping, right? And so what we need to do is we need to rotate these around so they're overlapping, right? So what would that look like? Well, we keep one side the same. I always start, and I start doing it where my hand's off the dang table and I can't keep a line. Okay, so, and then we need to rotate these, right? So the one going towards the top is still going to be in the plane of the paper. Okay? But what happens when we rotate something 180 degrees? Yeah, well, the things on the top go to the bottom, but does the thing in the plane going away from you stay going away from you? Do they? Okay, well, let's try it. So I have my mask. It has my little loops coming towards me, right? So I go ahead and flip it 180 degrees. My loops are going away from me, aren't they? Uh-oh. So, yeah. Remember, every time you flip 180 degrees with a group, what happens to the other groups? They flip, right? Yeah, it always goes left to right, goes to right to left, right? You have to reflect everything. Okay. So what does that mean for this? You can also look at it in terms of like rotating your hand, right? So we rotate our hand, and the CH2OH is on the bottom, right? We point our fingers that way, our palm is going into the other carbon. And then we use our thumb as our H, right? We rotate it 180 degrees so they line up. And which side is our thumb now? It's pointing towards us, isn't it? And so the H has to be pointing towards us. Can you see that okay? Okay. I know I'm like overkilling it sometimes, but I just want to make sure you understand and have multiple ways you can think of these things. Because not everybody thinks alike. So the H has to flip, the OH has to flip, right? Okay. And so that's what that should look like, right? So that means the OH and NH2, they should be on the same side, right? The H and the H, they should be on the same side. So that's okay, isn't it? So that is that. And so is, yep, that is it. That one. Okay. I'm going to go ahead and let you guys try this on. Give you a couple minutes. You try to match them. And then you guys are going to explain why. Or y'all. Let's get y'all. Come on. Go do it. You can do the homework problem while you're here. If you haven't already.